So in the last video, we derived the transfer function for a simple electrical circuit. Today I will be coming back to a mechanical system and derive the expression, the transfer function for transfer function for a rotational mechanical system. So our approach for transfer function is going to be the same. First we will be writing the governing differential equations and then taking Laplace transform, and then we'll finding the corresponding transfer function. So a rotational mechanical system is a simple system which has a shaft which receives some torque input from motor. Right? There is some input torque. Right? This shaft is being held on a conventional bearing. So this is a bearing. And then this shaft is attached to a load. Right? That load could be a gear. This shaft would actually be the manipulator of a robot. Right? It could be a gripper here, something like this. You have already seen this, right? Or it could be a geared shaft or some load attached here. So that load torque is, let's say, TL, and the moment of inertia for the shaft is given by J. This bearing provides some damping to the rotatory motion, and we'll be using B. I am using B here, which is quite unconventional, because as you must have seen the books in control engineering, it's a very multidisciplinary course, right? So even Professor Gopal is from electrical background. So most of the books that are written for control systems are written by electrical engineers. So the notations you will find are very unconventional ones. For damping we usually use D or C, but since in most of the books it's B, and so that you find it familiar when you open your books, I'll be also using B. Right? So if you want, you can take the torsional stiffness of the shaft as well, but we would be neglecting it. But if you want to take, you can take it in the form of G theta by L from your MOM course. Right? But we would be neglecting it because we consider that the torsionally the shaft is rigid and it does not flex torsionally. Right? So let the angular displacement of shaft be given by theta. Right. So I can write the equations of motion governing the rotational motion of shaft, and that will be J times theta double dot, or you can also write omega dot. If it's the omega that is your specific output, you can write this equation in terms of omega also. Right? Plus B times theta dot. This is the angular acceleration. This is the force from damping. B is the damping coefficient, I have already told you. Very unconventional nomenclature. Sorry, the variable used. And this should be equal to the torque into the shaft minus the load torque. This will be the governing equation for the system. Where now the desired output from the system is its angular motion. Mind you, this is very important, right? The angular motion in the case of, let's say, a conveyor belt, it has to be very precise. So you need some control over it. Then angular motion of a gripper of a robot manipulator is we want it to be very precise. Right? If the robot is used for picking and placing some object, even then we want it to be very precise. So you need to use feedback control in those cases. But feedback control will come later. First we need to model the transfer function of the system. Right? So your output can be theta if it's position control. Your output can be omega if it's speed control. Right? So now that I have got this equation of motion, I'll be using the same modus operandi, and that is that I will be taking Laplace transform on both the sides to find the transfer function. Right? That is what we did in a single degree of freedom system, that is what we did in the electrical system, and that is what we will be doing here also. So that is our method of finding the transfer function. So if I take Laplace transform on both the sides for this equation, what will I get? It will be, and for finding the transfer function, we usually assume, not usually, almost every time we'll assume that the initial conditions are 0, right? So this will be Js square theta s plus Bs theta s is equal to T in S minus EL S. Right? T in minus EL S. Isn't it? Now, we need to find the, let's say I take theta s common, let's say it's a position controlled kind of problem. So theta s will be equal to what? 1 by J s square plus Bs multiplied by D in minus 1 by J s square plus Bs multiplied by E. This could have been a speed control problem as well, right? Motors speed control, shafts. Then what would have happened? This would have been your omega s, and instead of s square, here you would have got s, and here instead of bs you would have got b, right? Because here it would have been j omega dot plus b omega, isn't it? Just a change of variables. So this is the final form of equation for theta. How can I show it in block diagram fashion? Very important. So that is, this is the input torque, this is the disturbance torque, you can call it in control terminology, or this is the load torque, and this is your dynamics of the shaft, and your output is